In the previous examples, I basically just gave you the controller to try, or we just picked it blindly. At this point, we'll now try and provide a few sort of guidelines to help us determine whether or not we should be attempting to add a 0 or a pole to our controller. Should we be attempting a PD controller or a PI controller, or what? In general, adding a 0 tends to pull the root locus towards the left, which tends to make the system more stable and settle faster. By moving the poles to the left, they have a larger sigma, so the settling time tends to be smaller. Adding a pole tends to have the opposite effect. It tends to pull the root locus towards the right, closer to the right half plane, so that the system is generally less stable, sigma is smaller, so the settling time tends to be larger. It settles more slowly. An exception to this is when you put a pole near a 0 or a 0 near a pole, and the effect of that is basically a pole-0 cancellation. So if you place a pole near a 0 or a 0 near a pole, it tends to reduce the effect of those poles and zeros. At this point, I'll now go ahead and open up MATLAB and try and show you how to use MATLAB to draw the root locus and to design controllers. Some of this may be a little fast or a little hard to follow. A reference that you can go back to is here's a web page that discusses the use of MATLAB for controller design using the root locus. You can also use the various help through the MATLAB software or the MathWorks website. So first, we'll create a system, a transfer function corresponding to the plant of the very first example that we looked at in today's module. We begin by defining the Laplace variable s. We can then create a transfer function. From the first example, that system had a 0 at -2, and it had a denominator of s squared plus 2 times s plus 3. And so we can plot the root locus of this open loop transfer function using the command rlocus. And so what this does is it treats g as the open loop transfer function, and it makes the presumption that there's a parameter k that's multiplying this open loop transfer function. And then it draws the root locus varying k from 0 to infinity. And so this is the picture that we recall. And in that example, what we were trying to achieve was pole locations with a sigma equal to 3. And so one way to do that, so you can see here -3, you can imagine a pretend line here, an invisible line here. If we come up here and click on this data cursor, what it does is, and then we click on the root locus and we move this around, it shows different points on the root locus, and it shows the gain, the value of k that places the closed loop pole there, tells you what the exact pole location is, and then it also tells you these qualities: damping, overshoot, and frequency. But these properties are only if that pole belonged to a canonical second order system. So in this case we have a 0, so the overshoot would not actually equal 2.71. But anyways, we're trying to achieve a pole with a sigma equal to 3. That is a real part of -3. So if we keep moving this cursor around, we can see that we have a pole that's close between these two locations here. There's a pole of -2.83 and there's a pole of -3.06. And in essence, those points that it's jumping between are the points that MATLAB calculated in generating the root locus. So recall that MATLAB generates the root locus in a brute force sort of manner. It starts at k equals 0, and it steps up values of k, calculating new closed loop pole locations, and then it draws a continuous line to connect the dots. If we want to try and interpolate between those 2 points a little bit, what we can do is the following. So we can right click, and in the selection style, instead of snapping to the nearest data vertex, we can go based on mouse position, and that will allow us to get in between values. So there I'm able to place the pole with a real part of -3, and you can see that the corresponding gain is 4. Here we had a plant with 2 poles, a pole at -2 and a pole at -4. So that's our transfer function. We can again use the rlocus command. This is the same root locus we generated by hand. Looking at this, you'll have to sort of imagine the region that we were looking for. Recall that it was a sort of a triangle that was above, it was above a horizontal line at pi and below an angled line at 45 degrees from the origin. And so right now this is too small to see the region, but we know that it didn't work. And we also knew that by placing a 0 out here to the left of -4, we thought we might have the opportunity to bend the root locus into the desired region. So now we can create a new transfer function with an additional 0 and see if we can indeed get the root locus bent into the desired region. And so we can create an entirely new one, or we can just take the one that we had and add a 0 to it. We want to be to the left of -4, so we'll just go ahead and try a 0 at -5. And we get the sort of shape that we were anticipating with this circle. So looking at this, we want to get above a horizontal line of pi. We're not there yet. We're below 2. So I'll go ahead and try a 0 that's farther to the left. So instead of s plus 5, let's try s plus 10. Look at the root locus, and that made the circle larger. And so now it's looking possible here. So here approximately is a horizontal line at pi, or around 3, and so we've definitely gotten our circle above it. And you can sort of imagine an angled line. So in essence, we need our imaginary part to be greater than pi, and we need our real part to be greater than our imaginary part in order to get it under the -45 degrees. And again, we can use this cursor, click on the circle. Here we've got an imaginary part greater than pi, and we've got a real part that's larger. So this indeed satisfies our requirements. And something like this might put us more safely in our region, or even something over here might put us more safely in our region. So this gives us our gain and our pole location. So it does appear indeed that we can use a PD controller in order to achieve our desired pole locations. Another command that can be helpful is the rlocfind command. So before we call this command, let's go ahead and go back to the original transfer function we had from the first example and draw the root locus for that system. If you recall, it looks like that. And then we'll call the rlocfind command, and on the left hand side we give 2 outputs, k and p, and on the right hand side we have the command rlocfind, where we give as an argument the open loop transfer function that we want to draw the root locus for. And so if we hit return, what it'll do is it'll take the root locus and it'll add these crosshairs, and what these crosshairs allow you to do, if you pick a point on the root locus, what will be returned is k, which is the value of the gain that places the pole at the location you clicked on, and then p, which is the location of all of the poles corresponding to that k. So for this example, we have a second order system. So if we clicked on one point, it would give us the value of k that places the closed loop pole at that location, but it would also return other poles. Since this is second order, it would return both poles that are placed by that value of k. So for example, we had discussed how if we had placed a pole exactly at -3, we would get one real pole at -3, but we would also get another pole out here to the left that was faster. So let's go ahead and click on this point -3, and we can see that the value of the gain that places us there is approximately 6, and it looks like we get a closed loop pole at -3 and another closed loop pole at -5. So this can be a helpful command. Another helpful command that is actually quite powerful is called the RL tool command, and you can also call it via the SISO tool command, but we won't get into that during this module. That's something we'll discuss later on. Returning to the PowerPoint presentation, that brings us to the conclusion of Module 18. In this module, we discuss how to use the root locus in order to design controllers, and in particular we introduced a procedure where we first translate performance specifications into closed loop pole locations. We then draw the root locus for a simple gain k for a simple proportional controller, and we see if that gain change can meet our requirements. In other words, we see, is there a value of k that puts the root locus in the desired region, that puts the closed loop poles in the desired region? If yes, then we're done. If not, then we try a more complicated controller. We try to add poles and or zeros in order to reshape the root locus to bend it into the desired region. We learned some basic guidelines that zeros tend to pull the root locus to the left, poles tend to pull the root locus to the right, and placing a pole near a zero or a zero near a pole tends to cancel out the effect of those poles and zeros.